So this lesson's on directional derivatives, and I want to first start by reminding you of partial derivatives and what they mean geometrically. So f sub x, the partial derivative of f with respect to x, is written as this funny-looking dz divided by dx, which is approximately the same as the change in z over the change in x for small values for the change in x. Now, how do we visualize this? Well, we think of a starting point and an ending point. Each of these is going to have an altitude on our surface. So going from here to here, the z's are going to change. So that'll be your change in z on top. And the bottom is going to be your change in x. So it's a sort of slope. What I want you to recognize is that we are moving in the direction of 1, 0. So that's going to be important for us. That in this instance, when we're moving just in the x direction, we're moving in some direction parallel to 1, 0. Similarly for f sub y, what we have there, partial of f with respect to y, is this dz dy looking thing, which is approximately the same thing as change in z over change in y for a small change in y. Here we're moving in the y direction from one point to the other. We would expect that our heights would change, so it'll be our change in z on our surface, and then our change in y is here. But I want you to recognize there that we're moving in the direction of what vector? We're moving in the direction of 0, 1. But what if we want to move in a different direction? What if we want to move in this direction? How would we discuss an analog of that? What's the idea? And that's what a directional derivative is. If this is my starting point and this is my ending point, we could imagine change in z. But what will we divide it by? It's not change in x, it's not change in y, it's change in distance. So that's what's going to define our geometric perspective of the direction. So here's our idea. This is our notation we use. The directional derivative of some function f at the point x naught, y naught in the direction of some vector u is approximately the change in altitude, the change in z, divided by the change in distance traveled. So let's look at a sample question. We want to approximate the directional derivative of this function. F of xy is 3x squared y plus 2x plus 4y at the point 1, negative 2 in the direction of 3, 4. So we're going to start at 1, negative 2. That's going to give us our initial z value by plugging it in here. And I'm going to move just a little bit in the direction of 3, 4. So think about how we're going to do that. To go to a new point, and then evaluate that in f to give us our second z. And then we're going to look at the change in z, the change in height, divided by the change in distance. How far did I actually walk? That's the idea we're trying to work on here. So here's my thought. I'm starting at the point 1, negative 2, and I want to move in some small vector in the direction of 3, 4. So I'm choosing 0.003, 0.004 to do an approximation for our directional derivative. So my starting point is 1, negative 2. But the next value that I'm going to is going to be 1 plus 0.003 and negative 2 plus 0.004. And we need to determine what's the height, what are the z values. Remember, the z's are the value of the function, which is what? 3x squared y plus 2x plus 4y. So let's go to a spreadsheet to help us do this computation. So I believe I programmed this correctly. So in my x value, I need 1 plus 0.003, which of course is 1.003. And in the y direction, I need negative 2 plus 0.004, which gives me negative 1.996. So now if I plug that into the function f, I get this. Notice very, very close to negative 12. So the change in z would be the second z minus the first z. Second z minus the first z. Let me fix my spelling of change here. And let's talk about our change in distance. What will that be? What's our change in distance? Well, we see that we are going in the 0.003, 0.004 direction. So how big is that thing going to be? If this is 0.003, and this is 0.004. There's my change in distance, which will be the square root of 0.003 squared plus 0.004 squared, which probably doesn't surprise you, is 0.005. So as we go back to the spreadsheet, what do we see? We'll make our change in distance 0.005. And then our DUF, that's the rate of change of altitude with respect to distance. So we're going to just go ahead and divide these two numbers to see what we get. Equals this number divided by this number. And our approximation is about negative 0.396. So filling in all the values, we have our approximation for the directional derivative. The change in altitude divided by the change in distance is about negative 0.396. That is an informal way to approximate it. Now let's go ahead and get a formal strategy. So we need to find both partial derivatives. I need to find both f sub x and f sub y. So let's do that. So f sub x, partial with respect to x of the first piece plus partial with respect to x of the second piece plus partial with respect to x of the third piece. 3y is thought of as a constant. 3y times the partial with respect to x of x squared plus the partial of 2x with respect to x is just 2. 4y is thought of a constant. That is 0. The partial with respect to x of x squared is 2x. 3y times 2x plus 2. 6xy plus 2 is f sub x. Now let's find f sub y. We've got that computation done. Partial with respect to y of the first piece plus partial with respect to y of the second piece plus partial with respect to y of the third piece. 3x squared is thought of as a constant times the partial with respect to y of y. Partial of y of 2x is 0 because 2x is perceived as a constant. Partial of 4y is 4. Partial of y is 1. Put all that together and we have f sub y is 3x squared plus 4. But I need this at my point of interest. My point of interest was 1, negative 2. So we need to figure out what is f sub x at 1, negative 2, what is f sub y at 1, negative 2. So plugging in 1, negative 2, 6 times 1 times negative 2 plus 2, negative 12 plus 2, negative 10. F sub x of 1, negative 2 is negative 10. Now to f sub y. And we get f sub y of 1, negative 2 is 7. And remember, we're going in the direction of 3, 4. So we're going to collect all of this stuff to determine that directional derivative. The next thing I've got to do is I've got to find a unit vector in the direction of v. So that unit vector would simply be 3, 4 divided by the magnitude of 3, 4, which is 3, 4 divided by the square root of 3 squared plus 4 squared. 9 plus 16 is 25, which is just 5. So I get 3, 4 over 5, which is 3/5, 4/5. So putting that together, then, how do we determine our directional derivative? What will our rule be? So here's our big rule. To calculate the directional derivative, you find the partial derivatives and take the dot product with the unit vector defined by the direction you're headed. So in this case, what do we have? The f sub x at 1, negative 2 is negative 10. The f sub y at 1, negative 2 is 7. Dotted with the unit vector, which is 3/5, 4/5. And where does that put me? What do we get? Negative 10 times 3/5 is negative 30/5. Plus 7 times 4/5 is 28/5, which equals what? Which equals negative 2/5, or negative 0.4. Now, how close is that to our predicted answer? Well, let's go back to the spreadsheet and see. We have a DUF here of negative 0.396, pretty close to our exact answer of negative 0.4, which makes me feel pretty good. So what are the highlights of this idea? The directional derivative of the function f in the direction of u is in essence the change in z divided by the change in distance. That's what we're looking for a relatively small change in distance. And if we're dealing with f sub x, the u that we're dealing with there is 1, 0. And if we're dealing with f sub y, the u that we're dealing with there is 0, 1. So f sub x and f sub y are in essence, right? They are in essence directional derivatives. And the rule that I just gave you was this will be f sub x comma f sub y dotted with the dot product of u1, u2, where u1, u2 is a unit vector. And that's the direction that we're headed, right? So certainly notice if it's 1, 0, fx comma fy dot 1, 0 gives me f sub x, and that satisfies that requirement. But keep in mind what it means geometrically. Change in altitude divided by change in distance traveled. Here it's change in altitude divided by change in x, but the change in x is change in distance traveled. Same thing here. Change in altitude, change in z, divided by change in distance traveled, change in y.